Hi there, everyone. I'm Vinicio Prado. I'm a Yachay Tech student, and today I'm going to present my linear programming final project. Okay, wait a moment while I show my slides. Here we go. Okay, in these lectures, we were asked to make a final project using linear programming. I choose diet programs because I used to go to the gym and work in calisthenic, I would say. But then because my some academic is responsibility I have to do, I have to stop it. And now I like to resume my activities at the gym. But for this I need to add also a diet that meets all the requirements that my body needs so I can grow muscles. Here's when I use the Mixer interlinear program to solve this problem. Okay, as I told you, when you make a body recomposition, you're targeting two objectives. First, fat loss. You have to all the fat in your body go away. You want to rid of them, and also grow muscles. But for this, you need some protein requirements in your diet. But what is the problem? I'm a university student. I have a limited budget, so I have to find the optimal solution of meet all the requirements of the nutrients my body needs, but spending the less I could. Well, for this, I use my basal metabolic rate and totally the daily energy expenditures. What is it? It's basically how much my how much calories my body consume when I'm in rest. For this, I use my data. My that I weigh 75 kilograms, 178 centimeters tall, and I'm 25 years old. Using this data into Mufflin-Sidger's equation, it gives me a basal metabolic rate of 1755 calories. But also I have to add an activity factor. As I live in Yachay, that it's all hills and mountains, I have to move through all the campus, be, and I have to make my gyms workouts. So it gives me a high activity factor of 1.725, would give me a 330 calories total daily energy expenditure. For losing fats, what I have to do is a caloric deficit. So I take off 180 calories of this TDEE. So my target would have a diet that had less or equal to 2850 calories. Moreover, as I told you, my body needs to meet certain requirements, as it is proteins, fat, and carbohydrates. Well, then I use these amounts because of scientific literature says that for the activities I would do, it is good to consume 2.2 grams proteins per kilogram of weight, 1 gram of fats per kilogram of weight, and the rest would be a target to consume in carbohydrates. Also, I add for this problem, I add some constraints for macronutrients because it's not my body don't work just with carbohydrates, proteins, and fats. It also needs minerals, vitamins, and other stuff. Here I choose four principal axes, so my diet could meet. It is for my neural system because when you are loading weights, you need that your muscle activates through certain ions. And here we go: magnesium, potassium, calcium, phosphorus, iron, etc. Also, the hormonal axis. To maintain an anabolic profile, it is I gain muscle faster. I need a, an increase in testosterone and a decrease in estrogens. So these micronutrients help me doing so. A digestive health. All these micronutrients could be absorbed and have a higher viability if I consume these other micronutrients. And for last, recovery and inflammation. To mitigate cellular stress, I consume omega 3, omega 9, antioxidants, glucosinolates, and vitamin K. Okay, that's the percent of the case. Now, how I work with that? Well, I went to the Grand Aki supermarket web page, and then I look for the items, the elements that call my attention. I create a dataset. Then this dataset went into a Python code. This Python code make three things. First, sanitization. For all the names the dataset has, it concatenates it in one name with underscores, as you can see. If it says aceite space de space oliva, then it concatenated all with underscore. Then we have normalization. It is the prices that I found was dollars per kilogram, but the amounts I was working with was 100 grams. So to align the price and the program could have a dimensional requirement, I normalize the price. And finally, I got the output matrices. We got the cost matrices, the macros, the set I that contain all the elements, and the macros matrix that is like pairs of elements and the macronutrient it has. Now, what is the MILP structure? We have a core function that is minimize objective function, sorry, that is minimize the sum over the total amount I have to pay for all the portions of elements I'm buying. And then for this we have two kind of variables. Continuous variables that have how much quantity of the food I'm buying, and the binary variables that says if certain element is included in the list of purchase I'm doing. And also the constraints. We have a constraint for each caloric, protein, fat, and carbohydrate requirements. Given that the amount of calorie I have to consume is less or equal that the target I gave you early. But the amount of protein, fats, and carbohydrate could be higher, as it won't affect, even though it would be better for me. And for last, the interior constraints say that for every macronutrients, the set of all elements that contain certain micronutrient, the sum must be greater or equal to 1. It is unless one element with certain micronutrients is included in the list. And for last, we have a lower and upper bound for the quantity I have to buy. At the beginning of this program, we have a background problem, sorry. That is that if we haven't upper bound, then the program concentrates all the element in some super elements that has like all the requirements I need, but it gives me a list of I don't know 4 elements for example, with this element accompanying all the list. And also I have to add a lower bound, so it won't give me unrealistic portion of food. For example, if the lower bound does not exist, then it could in order to fulfill the vitamin K requirements, it can give me like 0.001 grams of lettuce. That has no sense. Okay, and the final result. After running the code of with the dataset I got, I found that the better list of elements I can buy has a cost of $4.78 per day, which is very good for me. It meets my budget. I have no problem with that, and it meets also my targets, uh, calorie requirements, protein requirements, fat requirements, carb requirements, etc. All the content I add above. No, we analyze the result that the problem gives us. If it has a legume dominance, it is the most elements that helps me to meet the protein and carb requirements are lentil, peas, and beans. For the micronutrients, we have a fulfillment of vegetable like broccoli, spinach, cauliflower, and also we add mushrooms. And for last, to meet the fat gap, we add olive oil and chicken legs. That's it. But with this list of elements, it won't be enough. Also, I give a recommendation for a menu. As you would guess, in the breakfast, I add all the yogurt, all the fruits, and the eggs. It's a normal breakfast that you would get in a normal diet. For lunch, when you are in the middle of the day, you need to fulfill the protein requirement. That's when I add all the legumes and also some vegetables to fulfill my stomach. Then I add afternoon snack with some with a minister cucumber. So it could accompanied by cracks. That is not in the list, but it won't cost that much, so it doesn't matter. And for last, we got the dinner, but we have a rich uh, vegetable salad with tuna and beans, topped with some mushrooms, salt, with asparagus and olive oil. Now I analyze also some what if scenarios. For example, what if there's a shortage of certain item at Granaki? Would my program still working? Well, the answer is yes. If, for example, there's a shortage of rucola at Granaki, then their program just complement that with spinach and lettuce, adding eggs and cost. That is not that much, but the cost is still finding a optimal solution. Now, other scenario is what if I write this lower bound? Well, if the lower bound is less than 0.3, then the solution wouldn't have sense as for fulfill the micronutrient requirements, it will give me a microdoses, as I told you, that has no sense. If the happens that my lower bound is less than 0.3, then I get a better solution that have a cost of $1 and something, but it has no sense eating 0.1 gram of spinach or other vegetables. So for ensure variety, it's better that the epsilon is greater or equal to 0.3. And for future works, I also like to say I also like to work with, for example, allergy constraints, preference modeling, and stochastic forecasting. What is it? What if a person that is allergic to certain element would like to try my program? Then I have to add a new set that is the elements that are forbidden for them and give it to the program that the sum of all containers elements is 0. Also, adding a preference modeling. Um, for me, it's not a deal. I eat everything. But what if a person doesn't like tuna, for example? Then I add some ways that helps that the center item looks cheaper if or for like or have a expensive cost if it disgusts us. And also for last, the introduction of probability distribution to the cost, because as you know, the cost of elements are not fixed, but it changes through time because inflation and some seasonal price spikes. And that's it, guys. That's my final linear program project. I hope you like it, you enjoy this presentation, and hope you see you in the next time. Bye bye.